Vijay, now
Yeah.
you can directly start first.
Okay. Yeah. So welcome everyone. Very warm good afternoon. This is the 5th student lecture series today, being organized by SCSE Graduate Students Club. So first of all, I would like to briefly introduce what is SCSE Graduate Students Club and how we organize this event. So my name is Vijay Prakash Dwivedi and I'm the president of Graduate Students Club in SCSE. We are the official students body representing graduate students in the SCSE, our school. And as you can see in the screen, we have certain objectives to achieve and we volunteer our services in this club. So few of our objectives are to represent students' interests to the school, to the university and administration. We aim to promote interactions by organizing several welfare events and extracurricular activities. But it's not been possible since COVID started. So we will keep on adding events on that line after we improve the situation. Next, we also aim to promote platforms which encourage students and graduate students to share their research works or have a environment where they can interact with each other, so that it feels like a cohesive environment for graduate students in SCSE. So as part of this, we started student lecture series, which is the SLS. And in SLS, any graduate student in SCSE can volunteer and present their research work. For example, today we have today we are organizing the 5th SLS talk in the series, and GAO has volunteered to present his recent research that has been accepted at CVPR as an oral. And it's really competitive to get a paper accepted there. And a CVPR oral has, I think, around 4% acceptance rate this year. So it's a great work by GAO, and he volunteered to present his research today. So how you can, as a student, how you can come and present in this research? It's very open. If any one of you are doing some research and you want to present among the students, you can simply email to our official email ID. You can Google it, and we'll schedule a talk. We'll have such virtual Zoom meetings where you can come and we'll have discussion. The students will also receive feedback from other interested individuals. So this is about GSC and the SLS. And after the talk, if you have any questions, you can directly interact with GAO after he finishes his presentation. And this talk will be also hosted on our YouTube channel. The link we'll share at the end. So that's all from me. I'll hand over to Manoj, who will be hosting and moderating this session now. Thank you. Thanks, GAO, for volunteering for today's SLS. Yeah.
Thanks for
thank you.
Yes.
Thank you, Vijay. Thank you. And this is Manoj Sakya, and I'm the moderator of this session. So once again, welcome you all in this SLS talk, student lecture series talk. And let me welcome our presenter, GAO, as well. GAO, welcome.
Yes,
and yes, and you are talking about GAO. He's the first year student right now, but soon we'll be moving to second year, I guess.
Yes.
And his interest lies in the machine learning. He has a wonderful talk this afternoon, and we are very excited to hear you, GAO.
Yeah.
So
and
please,
I'm happy to.
Mike is all yours. Now you can start.
GAO,
okay.
You can please share the screen now.
Okay.
Yeah, you can share the screen. And yes, after the talk, we'll be having some question answer session. And I request all of you to mute your mic during the presentation. Thank you, everyone. Yeah, we can see your.
Okay.
Yes, we can see your slide.
Okay. And I'm glad to come here to present my recent work called Privacy Preserving Collaborative Learning with Automatic Transformation Search. And thanks for SLS give me an opportunity to present this work, and welcome our audience. If you have any papers published, then you can come this platform to present your research work. And this work is a joint work from Nanyang Technological University, SLS, Chongqing University, and Tsinghua University. It's a CVPR oral paper and has been introduced by Vijay. And first, this is today's agenda. I will introduce this paper from the following 4 points. First is about background and challenges, collaborative learning. And first, we will discuss the privacy leakage of collaborative learning. And collaborative learning is proposed to protect the user's data privacy because participant does not need to release their private data and still can optimize the machine learning model via sharing local gradient information. If you have any experience about the optimization of machine learning model, you know that gradient descent is very important to improve the model performance. And so, if you have a large model, if you have a large scale data set and you have a large model, you have to distribute it to train this model and then improve your performance. And then, so in distributed settings, you need to exchange the gradient information. And so the shared gradient information, however, the shared gradient information can be utilized to reconstruct the data via a kind of attack called reconstruction attack. And many research work such as DLG, deep learning gradients, IDLG, improved deep learning gradient, and inverting gradient. This method can recover input through various optimization methods, and this allows us to prevent this kind of attacking threat. And the gradient sharing can leak the data privacy, and this is the reconstruction attack pipeline. And in the normal settings, the normal participant send input into the differential model and then backward, and backward, and then it gets the gradients for parameters. And at last, it needs to share the gradients for other participants or other machines. However, at this time, there is a malicious attacker, and they can utilize the this gradient information to reconstruct the images. And we can find that by optimizing the gradient difference, and it can optimize and it can utilize the various optimization. Optimization such as the optimization methods such as SGD or ADAM or LBFGS, something like this, to minimize this objective, and then it can recover the input image and also the label. And notably, we find that inverting gradient can recover high fidelity image results. We can find that the left image is the original image input images, and the right image is recovered by this pipeline. And we find that the recovered image is very clear. And and so we know that this is a kind of a threat for our input data privacy. So what about the existing solutions and the corresponding gaps? And if we want to protect the data privacy, differential privacy method occurs to our mind. It is a very classical and well-known and important method in privacy preserving area. And the idea is very simple, or the method is very simple. Just add the Gaussian or Laplacian noise on the shared gradients before sharing it with other participants. However, this method has following drawbacks. It cannot trade off the model performance or model accuracy and the data privacy. And this image, if we want to guarantee the model performance, we can find that no matter we add noise or not add noise on gradients, the image still can be recovered. And another way is called as a gradient compression. It can be taken as another kind of differential privacy. And And the method can be derived from the name. Gradients with smaller magnitudes are proved to 0. This method can be widely used into distributed training to reduce the communication cost. And in these settings, it still cannot balance model accuracy and data privacy. The last method is called gradient encryption. It utilizes the cryptography to protect the data privacy. And this method, such as the secure aggregation or homomorphic encryption. However, this method are not very compatible with most convolutional neural networks and other learning systems. And furthermore, this gradient encryption is very time-consuming, especially in our latency-sensitive system. So now we find that we lack a generic way to trade off the model performance and the privacy for the collaborative learning. And so next is about our proposed solution. We want to utilize a very simple idea, data transformation, to defeat the reconstruction attacks. And why data transformation? In AI security problem, there are a lot of research works about the image transformation, and they utilize this image transformation to mitigate the potential threat, AI security threat, and such as adversary attack. Xie proposed the input diversity method paper to mitigate to define the adversary attack to adversary examples, and such as the backdoor attack and watermarking attack. The Core and Manning and Qiu Han and Guo Shangwei, they propose to utilize the image augmentation to obfuscate the input data to prevent potential attacks. And so this inspires to utilize the very simple data transformation to see whether it can defeat the reconstruction attacks in our settings. And another motivation is that current methods cannot trade off the model performance and data privacy. However, from machine learning practitioners, they have the implication that data augmentation always can improve the model performance. And recently, a variety image transformation have been designed for better model performance, such as a mix-up or auto-augment. And furthermore, here is auto-augment is proposed by Google, and they utilize the auto-ML idea to search a combination of basic basic augmentation technique to improve the final model performance. Now, our problem is become can we utilize the data transformation to defend reconstruction attack? And in image transformation area, we have a lot of image transformations, and such as the rotation or shift or the construct or make it black or either some random noise on the image, and a lot of naive image transformation to wait for us to select. And similar to the previous, I mentioned the defending methods. It still has the difficulty in trade-off. And for weak image transformation, for reconstruction attack still can recover the input images from the released gradient information. And for strong image transformation, such as with a very strong noise very strong Gaussian noise onto the input images. It could lead to the degradation of model performance. So how to strike a balance is the key issue to select the image transformation. And before we introduce how we can select a good image transformation, we need to define image transformation policy. It is the set of transformation functions for T1, T2 until Tn. It is all of them are the very basic image transformations, such as rotation or shift, something like very basic image transformation. And they are not, this transformation is not a strong transformation, but we want to combine them together, make to find a very sweet zone data augmentation technique, techniques. So our objective is to become such the most privacy preserving and efficient image transformation. So as I mentioned, our paper title is automatic transformation search. Here is our pipeline of the automatic transformation. The first step, we need to sample the transformation policy from the Augmentation Library, and we utilize the open source the released Augmentation Library and on GitHub from GitHub repo. And then we calculated the accuracy score. And what is accuracy? I will introduce later. And then drop the policy T when the accuracy score is less than our predefined threshold. And we can take the step 2 as a filter to filter out the too strong image transformation and to guarantee the model performance. As the third step, we compute the privacy score. And this is the biggest contribution in this paper. And I will introduce it in later slides. And finally, we need to select the best transformation with the smallest privacy score. This is the brute force search. And because why we utilize the brute force search, why don't we utilize the IL or something else, some heuristic search method? It's because in reconstruction attack settings, the evaluation step is very time consuming and expensive. If we follow the paradigm of the classical paradigm of AutoML, train it and evaluate and get the final performance, it is a very time consuming and it is more expensive than the normal AutoML to search the best model. And so we want to utilize a lightweight prox function to measure the model privacy ability. And if we find that we find a good lightweight prox function to measure the privacy ability of augmentation, and then we find that the brute force search is okay. So this is why we don't utilize other fancy methods such as IO or genetic programming, and because this is the brute force is okay in our settings. And next is privacy score for automatic transformation search. This is the biggest contribution in our paper, and we start from this motivation example to introduce the privacy score. The x-axis is the linear interpolation of input x and a random noise x0, and so the y-axis is the gradient similarity, which measures the gradient similarity of interpolated input x prime and the clean input x, and the gradient similarity is measured by the cosine similarity cosine metric, and we find that blue line reduces the difficulty of the adversary to find the correct direction towards the transformed data, and in contrast, orange line gives the adversary an indication to discover that the correct moving direction, and steadily make the interpolated input x prime approach the clean input x by minimizing the gradient distance. This motivates us to use the area under the curve to evaluate the privacy preserving ability of any augmentation. So we derive the equation of x prime, and here is x prime is approximate of the area under the curve. And so we want to know whether there exists a correlation between our proposed privacy score and the privacy preserving. We noted that we need to find a metric to quantify the privacy score. If we want to quantify the privacy preserving, if you want to measure the method whether a method is robust to attack, you need to select a very strong attacking model. Here we select the inverting gradient. This method can even recover the ImageNet results. And we also need to make a metric to quantify the recovered input images and the clean input images, the similarity. Then we utilize the peak signal to noise ratio, quantifies the visual similarity between reconstructed images and input images, which we find that here is a very positive, has approximately linear positive correlation between the privacy score and PSNR. This means that our privacy score is a good proxy function to measure the privacy preserving ability. Otherwise, and furthermore, our privacy score is a very lightweight, and it can be calculated in 10 seconds, and we can distribute it to such a large scale, to such a large scale image transformations without much time cost. Next is about accuracy score for automatic transformation search. This idea is inspired from the NAS without training paper. It is a SAML paper. Has been accepted by this year's SAML, and we want to repurpose it for our transformation search. In NAS without training, they propose a lightweight metric to find a good architecture. And in our case, we want to find a good data transformations, and we find that not without training, they propose a method can effectively apply in the architecture search, but for transformation search, their performance is not very good, and there's no very clear correlation between the model accuracy and accuracy score. So we utilize accuracy score as a filter to filter out the very too strong data augmentation, which could lead to the poor performance of model, poor model performance or poor model accuracy. And here is the three steps of the accuracy score calculation. The first step, we need to prepare initialize the model and calculate the geography metrics for the transformed input. Note that here x1, x2 until xn is the transformed data. Is the transformed data. And the second step is compute the correlation matrix as the following equations. The third step is to select the eigenvalues of sigma and calculate the accuracy score. And for detailed explanation why this accuracy score can work, you can reach this paper to find more. And here I give a very heuristic explanation is that here's the eigenvalues. The eigenvalues and for the input images, way forward and backward and get the gradients for input images. for if the input images for the gradients information for input, it has a large variance. We think it is a good. It is this model can be trained, can be optimized very well. If the input gradients, the variance is too small. If the variance is too small, we think it is not a good. This model cannot be trained very well. And what about the correlation between the privacy and accuracy score? We computed the privacy and accuracy score for each sample transformation policies, and we find that there's only a small portion of augmentation policy can contribute to the can trade off the model performance and the privacy preserving. This means that we cannot randomly select augmentation policy to guarantee the privacy preserving, and also make sure the model performance is very well. So next is about the experimental results. And here is the evaluation settings. All data set and models. The dataset including the CFA100 and the ResNet 20, CFA100, and the dataset includes the CFA100 and the fashion minist, and the model includes the ResNet 20 and the 8-layer ConNet. Our attacking implementation includes we follow the format of optimizer and distance measure. Well, I have introduced the pipeline of the attacking reconstruction attacking, and for different papers, they propose different optimizer and distance measure to improve the reconstructed images fidelity. And here we utilize the five attacking methods: LB, FGS, plus L2, and so on. And we notice that Adam plus the cosine is the best reconstruction attacking method, and it is also called as the inverting gradients. I have mentioned before, it is the very strongest attacking method, and it even can recover the imaginary results. Our defense, we also compare our defense method with other methods, such as the different magnification of Gaussian or Laplacian noise. It is a differential privacy. It inspired from its differential privacy idea, or different magnifications of a gradient compression. And we also compare our results with some random augmentation. We use the average result from 10 different random augmentation policies. Here's the evaluation results. The left visualization results illustrate the comparison of reconstructed images with and without the transformations. The adversary can recover the images with very high fidelity in the second row, and in contrast, after the training samples are transformed in the third row, the adversary can hardly obtain any meaningful information from the reconstructed images in the first row. The table reports the quantitative results under inverting gradient attacks and model accuracy. We observe that the searched policy can effectively reduce the deep leakage from the gradients, and the hybrid policy it means that if we only apply one single data augmentation, it will introduce the domain shift problem. For example, if we always make the image more darker, and if we evaluate in normal settings without apply the dark augmentation policy onto the images, the final performance will drop. So we want to make this domain shift the problem, and we select the hybrid method. Just utilize the above two augmentation methods to improve the final accuracy score, improve the final model performance. And similar with the fashion minist on ResNet 20. And the hybrid policy can exhibit the higher generalization ability on the final model, and more results and discussion can be seen in our paper. And last is about robustness, transferability, and comparison to other defense methods. First is a robustness towards various attacking methods. We find that our defense method can be effective on the different attacking methods, and so this means that our method is not just specific to inverting gradient. It can be generalized to defend other existing attacking method. Our attacking method can also have good transferability across data sets. Then we find that we can find that we use the same search policy from this table, and our result can still our accuracy performance and the privacy preserving ability is still good. This means that we cannot search a policy from a small data set and then transfer it to a large data set, or vice versa. And we also comparison with the other defense, and we find that our method outperforms the existing naive defense methods. And we also dive into the network layers, and we find that find whether our data augmentation can work. We compare our method with three strategies for node data transformation, for random transformation, and our search transformer policies. The y-axis is the gradient similarity. The x-axis is the iteration. We for each step we calculate the gradient similarity for each input images, and we find that the optimal policy makes it difficult to reconstruct the low-level features. And this for these two layers, this is the first two layers for ResNet 20, and we find that there's a significant gap between the search method and the random search transformation and the random transformation, as well as the node transformation. The gradient similarity is very large. And however, in higher level, in deep layers, the gradient similarity is similar. This means that our image transformation can obfuscate the input images about the low-level features, such as the input, such as the color, shape, texture. However, it can still preserve very good semantic information. And what about our searching and our training overhead? Our search cost is only required 2.5 GPU hours for 1,500 image transformation policies. And in contrast, if we apply a reconstruction attack for 100 images, it requires 10 GPU hours. This is a very time-consuming. So for naive AutoML, it's not practical. For training cost, we find that the training transformation policy can slightly slow down the convergence speed on the training set, and the convergence speed on the validation sets are identical. So the convergence speed, the training cost is minimal. So conclusions. Our study policy can prevent information leakage from the shared gradients, and our extensive evaluations demonstrate that the identified policies can defeat existing reconstruction attacks with negligible overhead. Our identified policies can enjoy high transferability across different data sets, and it can also be applicable to different learning systems. And this is a QA session.
Thank you so much. Thank you so much. That was a very wonderful presentation, and I think the work that you have presented here is really, really wonderful. Very appreciable work. Well, it's published in CBPI as well, right? Yeah, and I'm really impressed that the way that you presented your work, like first you introduced the concept, and then you also described like what research gap is there, right? And then the proposed solution that you have worked on, and some of the experiments results. that you showed. Like it follows a very wonderful sequence, and it was really, really easy. I mean, although me and some of my, definitely some of my friends are not that, expert in this field, but it was really, really comfortable and easy to understand some of the basic parts of your presentation. Where you mentioned like there are so many things inside your work. I mean, it's a really hard work. We can feel that one. So let's receive some of the questions from the audience, right? And Gawe is ready. Please, you guys can ask a question. Vijay, you are already on live, so I think you have a few questions, I guess. Please go ahead. Go ahead.
Thanks, Gawe.
Yes.
Great work. Very, very rigorous experiments and a lot of things. So thanks for the presentation. I was wondering, like, if I understand correctly, is the methods that you propose applies to like other tasks also, like except for computer vision? And if yes, are the same methods transferable or applicable to, for example, NLP tasks, for example, other data sets like graphs? And if not, like what are the changes that would be required to be done if someone wants to port these kind of methods to other tasks? Thank you.
Oh yeah, a very great question. And for images, it has a good properties that it is a continuous space, unlike the graph structure or NLP area. In NLP area or graph structure, graph area, it is a discrete space. So if we want to apply the data augmentation onto the NLP problem or graph problem, it may be difficult because the potential data augmentation space is not large. It's not larger than like the computer vision area. And we have put the NLP or graph augmentation search in our future direction. However, it is very hard to achieve this.
But this, yeah, thank you. So, but the same policy and hybrid methods would work. Like, let's assume there are some standard data augmentation techniques or transformation techniques established in other fields. So, the same policies will work, right?
Yeah, the same policy will work in computer vision area.
Okay.
But for NLP, I'm not sure, and I have no recent experience about NLP, so I cannot give you a promise about whether it can work or not.
All right. Thank you so much.
And yeah. Any other questions?
Yeah.
Hello.
Gawe, maybe, yeah, Chi Yao Liu, right?
Yes.
Yeah, please go ahead. Go ahead.
Okay. Thanks for your excellent presentation. Because you mentioned that the data transformation technique can be used to protect the privacy, right?
Yeah, right.
Gradient privacy. So I'm not sure if I understand correctly. In your slide, page 13, can you move to page 13? Yes. You mentioned that the data transformation policy is sampled from Augmentation Library, right?
Yeah, right.
Yeah, yes. I was wondering, what is the Augmentation Library? How does it look like?
Oh, yeah. Augmentation Library
from the library for data transformation.
Yeah, we also.
This is
we utilize the existing GitHub repo and utilize the augmentation from this GitHub repo.
Okay.
And they propose many basic augmentations like rotation or contrast or shift. And this is we can take them as automatic atomic data augmentation. And then we construct a series data augmentation like this page. T1, T2 until Tn is they are the atomic basic transformation, and we want to find a strong transformation. T is a combination of basic transformation.
Okay. What is the n? How do you decide the value of n?
Oh yeah, we just set the uplift as the we just utilize you can try it, and for 1, 2, 3, 4, 5, and then you can find for five out the augmentation, and the search policy always degrade the always decrease the model performance, and so you will reject the and you will set the n as 3 instead of 4. And because if you increase n, your search policy will become strong, and your search policy will become strong, and then it will degrade, undermine the model performance, and you can just have parameter search, but you don't need to spend a lot of time on it, and you can just try several values, 3, 4, and then you can find 3 is okay, 4 is not okay.
Okay, I see. Thank you.
Thank you.
Gawe, thank you so much. Let me receive a few more questions. If there is anyone with a query, you can unmute your mic and then please forward your question. If there is no one, Gawe, let me ask you one more question, one more query, just a query, just a concern. When we talk about different algorithms, and if there is like, one algorithm that follows brute force search or brute force mechanism, we usually think that this algorithm is very, very expensive in terms of, computations, or computationally it requires a lot of time. So in your experiment also, in this mechanism also, why this brute force? Why not an alternate method for the brute force search? Do you? I mean, if you have like another alternative to brute force, that might improve the computation expense.
You mean we utilize other search method, IL, or right?
Yeah. I mean, in the same slide.
If we utilize the IL or genetic programming, this heuristic method, we have to train a model, and we don't want to if for a paper you can try many fancy method to try many fancy method to make your paper eye catching, but but I don't want to spend much time on such method design, and finally we find brute force is okay, and so I think we don't need to design other such method and to spend much time on it. Furthermore, if I really design a method here or some other heuristic method here, we have to compare our method with the brute force, and it will increase the burden.
Okay. Yeah, I got it. Thank you so much.
And I will share another experience. And unless the problem is very special, in most cases, random search is okay. From my personal experience.
Oh, okay, great. So I think we are now at the end of this SLS talk. If there is no more further questions, I think I still have one very short request to Gawe. So if someone is really interested in your paper or in your work, so what other future works I think a researcher can move on with?
Like VJ said, NLP or graph structure, they are very challenging. And if you still hold on the still insist on the computer vision area, what about the other search method, not just augmentation, such as the search the architecture, something like this. And furthermore, I have a small discussion with my supervisor, and he think mix up. Maybe we can emerge mix up idea into our into our paper, and because we plan to submit a journal, and so we need to increase the content for this paper. And we try to immerse integrate mixed up into our paper and then increase the content. So maybe this are potential future directions.
Yes, Gawe, thank you so much once again, Gawe. It was really a great time. I mean, having you here with SLS Talk 5. So hopefully very soon we'll be having another SLS Talk 6, and we'll invite some of the wonderful people around us. And I'd like to thank all the audience who joined this SLS Talk. Please do support us, continue watching us, continue having discussion with our research work. Vijay, do you want to add a few more points here before closing the session?
No, I would like to thank Gawe, and I think you can take the charge for concluding the session. Yeah.
Thank you so much, Vijay. So as always, it's our great pleasure to have Gawe and all the audience here. Once again, thank you all. So hopefully within probably a month, we'll have another SLS talk. And guys, be safe, stay safe, and let's meet next time. Thank you, everyone. Thank you so much, Gawe. Thank you.
Thank you.
Thank you all. Okay, bye-bye. Take care, guys. Bye-bye.